Okay, earlier we got kind of through the periodic table there, and we were talking about some periodic trends. And really, a lot of the periodic trends that we talked about really are sort of the basis for a lot of the bonding that occurs, and also obviously some of the other interactions that we talked about in chapters after that. So I think the next sort of topic that we talked about was really a pretty big topic, which was bonding. We talked a lot about different aspects of bonding. So let's just get into that then. Bonding. First off, we sort of talked about sort of the basics of some different types of bonding that we talked about predominantly throughout this semester. One major type is obviously ionic bonding. And ionic bonding, as we've talked about many times, is usually between a metal and a non-metal. And it's an ionic bonding where we do have that transfer of electrons. And the result of that is our metal becomes positively charged, or a cation, and our non-metal, which gains the electron, or electrons, becomes negatively charged in our anion. And remember that the importance of sort of ionic bonding is the idea that these two guys are held together by the electrostatic attraction, which is a fancy way of saying opposites attract, basically positive, negative guys attract. But there's absolutely no sharing of electrons here, right? And that's an important distinction between ionic bonding and the other sort of major type of bonding that we talked about, which is covalent bonding. Covalent bonding is between two nonmetals, and two nonmetals we have basically sharing of electrons that occur. And as we talked about, the sharing of these electrons may be equal, which is a non-polar bond, or they may be unequal sharing, which would be a polar bond. To answer your question, I think it will probably be posted after this, I think. Now, what allows this to happen really is, as we talked about, really those kind of differences in those periodic trends, right? Because if we think about the periodic table, metals on the left-hand side, non-metals on the right-hand side, you have a very big difference between those sort of properties where the metals want to give away their electrons, the non-metals want to take the electrons. So we do get that full transfer of electrons in ionic bonding. For covalent bonding, it's different because they are both kind of in the same location on the periodic table, which means they do share very similar periodic trends, which means they both essentially want to kind of share electrons. So the best that they could do is actually that sharing, as they both really, I misspoke there, they both really want to take the electron. So they sort of compromise by sharing of electrons. So major difference between the two types of bonding that we talked about this semester: ionic, no sharing of electrons, complete transfer, making ions, covalent bonding, obviously sharing of electrons. And again, as we talked about, different sharing aspects of it, could be shared equally, could be shared unequally. We represent bonding a lot with using Lewis dot symbols or electron dot symbols. And we definitely can use these guys to represent, for example, ionic bonding. For example, the number of valence electrons is equal to the group number on the periodic table. So when we take something, say, like sodium, it has one valence electron. If we look at the configuration for sodium, it is neon 3s1, and that is the valence electron. And if we put that together with chlorine, which has 7 valence electrons because it is group 7 on the periodic table, and its configuration, which is neon, 3s2, 3p5, and that's its 7 valence electrons. What's going to essentially happen here, right, is the electron is going to be transferred in the case of sodium over to chlorine. The resulting is that sodium has now lost an electron, becomes positively charged. The chlorine picks up that electron and now becomes negatively charged. Remember, when we draw sort of Lewis structures for ionic bonding, this is what it should look like. It should definitely have the charges in there to indicate that there's no sharing of electrons. Sometimes people put a bracket at least around the negative guy. Sometimes people put the bracket around both. But in addition, what we see happen, and really the basis of all bonding, is the sodium has lost an electron, which means now this sodium over here has neon's configuration. The chlorine gained an electron, which means it now moves forward to argon's configuration. And again, really the ultimate basis of all bonding, as we talked about, is the goal to reach noble gas configuration. And in the case of metals and nonmetals, they do that by losing electrons and gaining electrons, and again, allows them to reach that noble gas configuration, because everybody really wants to be like the noble gases, which is, again, our group 8. And obviously the 8 is an important number because that is the octet rule, right? Which basically means that everybody wants 8 valence electrons except hydrogen, right? Which should only have 2 electrons total, because hydrogen only needs to get to helium to make it to a noble gas configuration. So that's sort of ionic bonding. And covalent bonding, again, we do have the sharing of electrons that occurs. So when we look at something, say, like F2, for example, that we've seen, F2 would be something that looks like this. And remember, there's different types of electrons that we talked about. All these dots that don't have any atom next to it are what are referred to as non-bonding electrons, are sometimes referred to as lone pairs. And obviously the electrons here are what are referred to as bonding electrons, which obviously are part of a bond. Remember that you could also, if you want, instead of using lines to represent bonding electrons, you could use dots to represent bonding electrons. So you can do either one. Most people do use lines. Again, one line representing 2 electrons or a pair of electrons. 2 lines would represent obviously a double bond, and 3 lines would represent a triple bond. But in this case, they're actually sharing electrons. And again, those electrons in the middle here account for the fluorine on the left, and the electrons in the middle there account for the fluorine on the right. And by doing so, they have now both hit 8 electrons. And again, that allows them to meet the octet rule. And again, really sort of get to that noble gas configuration. Remember that in this particular case, because they are both fluorine, we would expect these electrons to be shared equally. And this would be what is considered a nonpolar covalent bond, or just simply a nonpolar bond that most people would call it. And that's not always the case, right? Because if we kind of swap out, as we talked about, one of those fluorines for a hydrogen, we now have sort of this situation happening, which again could be represented by with the line or the dots here. And in this situation, the fluorine here has 8 electrons. The hydrogen, by sharing electrons there, ends up with 2 electrons. That 2 electrons is sometimes referred to as the Duet Rule, which is, again, what hydrogen needs to get to, because it just needs to get to helium. Fluorine here with its 8 valence electrons, again, making the octet rule. But because of this difference, these are two different elements here, and we know that fluorine is the most electronegative element. These electrons are not going to be shared equally. They're going to be moving closer to the fluorine because it will be attracting those electrons, creating a charge difference that can be represented by this arrow, where the fluorine becomes more partially negative, hydrogen becomes partially positive. They are still sharing the electrons, but they're no longer sharing it equally. And this makes this a polar covalent bond, or just simply a polar bond, it's sometimes referred to. And we have this unequal sharing of electrons. So they're still sharing, but they are sharing unequally. And that again creates this sort of charged aspect to this bond, where in this case here, where we have equal sharing of electrons, really no charge aspect to it. How do we know in terms of this, are they going to share sort of the electrons equally, unequally, or they're going to be kind of a transfer of electrons? We could use electronegativity values, as we talked about, that Pauling came up with, which goes from 0 to 4, 4 being the most electronegative. And remember that if you have a difference in electronegativity that goes from 0 to 0.4, that's considered a nonpolar bond. You have a difference in electronegativity that goes from kind of above 0.4, so like 0.5-ish probably and above, to below, again, below 2. You have a polar bond. And if you have electronegativity difference above 2, typically, that is going to be an ionic bond. Remember, as we talked about, you really don't need the electronegativity difference for an ionic bond. Pretty much, if you see it is a metal and a non-metal, you know that it is going to be an ionic bond no matter what. So really, a lot of times we'll use it for these two, polar and non-polar aspect of it. So for example, if you had fluorine, which maybe has an electronegativity difference of our electronegativity value of 4 minus hydrogen, maybe at like 2.1, you get an electronegativity of 1.9 for this bond here. And that tells us that it is going to be a polar bond, as it's above 4.4 really, and below 2. And again, you could use that. Remember that also if you have somebody that's in the same group or somebody that's in the same period, you also don't need the values. So for example, if you're comparing, say, we have nitrogen, oxygen, fluorine, we know electronegativity increases this way on the periodic table. So if you're comparing between nitrogen and oxygen, you don't actually need the values. Oxygen is more electronegative than nitrogen, and it will create a polar bond. Same thing if you're kind of comparing things downward in a group, electronegativity increases as you go up. So if you're comparing oxygen and sulfur, oxygen is higher up, so it should be more electronegative than sulfur, would create a polar bond. Remember, the only ones you have to worry about sometimes, if you're concerned, is sort of that diagonal relationship. So remember those sort of diagonal relationships where it's not really diagonal right next to each other, but it's kind of like diagonal and over one. Those guys are, again, one is further up, but one is further to the right. So they kind of diagonally cancel out their differences, and they actually end up with sort of the same electronegativity values. So, but for the most part, in a lot of situations, you probably can safely use the general trend in electronegativity to help you answer, is it going to be polar or non-polar sort of bond? Any questions on that there? So that led us really to sort of talking about how to draw Lewis structures for covalent compounds. And remember that when we draw Lewis structures for covalent compounds, there's several steps that you do want to follow. And you do want to kind of follow drawing those Lewis structures for covalent compounds. Like we talked about, You don't want to do piecework so that you end up with sort of the wrong picture. Again, you don't want to double bond or triple bond out of the box. Again, you remember, you just want to kind of start with the right skeletal structure. And that's just the logical arrangement of the elements. Remember that the least electronegative atoms in the middle, no hydrogen in the middle, no fluorine usually in the middle, but the least electronegatives in the middle. Usually most of the time, everybody else is attached to that central atom. The really most important thing is actually the total number of valence electrons, right? The total number of valence electrons that you have is really the most important. Remember, after you got the arrangement of it, you got the total number of electrons that you have to use. That number is important because your picture should have exactly that number, no more, no less. Then you want to make really a single bond from the center atom to each of the outside atoms. And then at that point, you're still going to have electrons to put onto your picture. So all those remaining electrons go on the outside atoms first in pairs, then to the center atom, also in pairs. So what that means is, as we talked about, you want to fill up everybody on the outside in terms of Octet Rule. If you happen to fill up everybody on the outside and you still have electrons to put onto your picture, then you go to the center, put it on as pairs of electrons, dots, basically, on the center atom. At that point, you probably should place all of your electrons there. You want to check that everybody meets the Octet Rule. And if they don't, at that point, that's where you want to kind of fix it by making a double bond or making a triple bond, right? And remember that when we make a double bond or a triple bond, we're actually moving those electrons in to do so. We just don't put extra electrons on so we don't have too many. And again, if you sort of follow those rules, you'll probably end up with a fairly good picture most of the time. So, you know, if we look at something like NF3, for example, again, nitrogen has 5 valence electrons because it's group 5. Fluorine has 7, and there's 3 of them. That gives us 26 valence electrons. Nitrogen is in the same row as fluorine, it's least electronegative. Fluorine can't be in the middle either. So we make a logical arrangement. Again, 1 bond, 2 bonds, 3 bonds. That is 6 electrons. That leaves us 20 to go, again, as pairs on the outside, 2, 4, 6, 8, 10, 12, 14, 16, 18. We have now filled up everybody on the outside with 8. We still have 2 more to go. Again, we place them on the center as pairs. We now check and make sure everybody has 8 valence electrons around them. Again, 2, 4, 6, 8 for each of the fluorines. Nitrogen, 2, 4, 6, 8. Everybody has 8 valence electrons. Remember that, you know, again, if we drew something like carbonate there has 4 for carbon, 3 oxygens, that's 6. Something with a -2 charge means that it actually gained 2 electrons, and you do need to include it in your calculation to give you 24 valence electrons. Here, we would follow the same approach. Single bond out, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. At this point, we have now put all 24 electrons. Again, our carbon is short, 2, 4, 6. So again, we take a pair of electrons, for example, and we bring them in, and that gives us a double bond here. Remember, you could have double bonded to the right. Could have double bonded there to the left. And when you do have multiple places where you could do that, these are what are referred to as resonance structures, right? Resonance structures are structures that basically represent a Lewis structure or a compound with multiple Lewis structures because the real structure is somewhere in between them. And the reason it's somewhere in between them really involves the double bond electrons. They're what are sometimes referred to as being delocalized, which means at some point they may be up here bonding there, but then they may be over here, or they may travel over here. So we get one of these three sort of guys that sort of represents, you know, the real structure somewhere between probably all three of them, but you could draw one of those guys there. Any questions on, again, that's sort of the proper way there to draw Lewis structures. We also talked about some exceptions to the octet rule. There's the incomplete octet, which is the one that we see the most sort of in this class. And the incomplete octet, I'm sorry, not the one we see the most here. Incomplete octet is one where we have less than 8 valence electrons. Boron is a pretty good example of a guy that sort of does that. It's sometimes referred to as being electron deficient. There's also an odd number of electrons, and that's where you kind of, you know, have an odd number. So when you're drawing your Lewis structure, you end up with one sort of unpaired electron present. That is what is sometimes referred to as a free radical. And they're very, very reactive. And now the one that I meant to say earlier there is the expanded octet. That is the one that we saw the most in this class. And that is the one where we do have basically more than 8 electrons around it. And remember that the people that could sort of do that is, if you look on the periodic table, there's sulfur kind of to the left, to the right, and then down. They have the ability to do that because sulfur, again, as we talked about, it's on period number 3, which means its end value is 3. And again, see everything coming back there to our quantum numbers. And because on the end value is 3, that means that L can be 0, 1, or 2. That means we can have an S, a P, or a D orbital. And it is the availability there of our D orbitals to those guys that it gives them really some extra room to house those extra electrons. So we can go upwards, as we saw, you know, 10 electrons, 12 electrons, or 5 electron pairs or 6 electron pairs around the central atom. And again, it's because those guys, you know, kind of have those extra orbitals that they could house them. That's also why we talked about, though, that the kind of period before this sulfur on the periodic table, where we have nitrogen, oxygen, fluorine, and those guys, they have to obey the octet rule, because at n equals 2, that means L is 0 and 1, which means they only have S's and P orbitals available to them. They do not have those extra D orbitals available to them that would allow them to accommodate the extra electrons. So definitely those guys have to obey the octet rule. Again, sulfur and below can go over it. Doesn't mean you need to go over it all the time. It doesn't, but it does have the ability to do it. This also explains how come we could have something like SF6, for example, and that would be 6 plus 6 times 7. That's a lot of math there. We'll go with 48 electrons. Again, sulfur would be in the middle, fluorine sort of arranged around it. That's 6, I think. We'll do a bond up there to everybody, and then basically we would fill in everybody with some electrons here. And in this particular case, again, everybody meets the octet rule. Sulfur here in the middle, 2, 4, 6, 8, 10, 12 electrons around it. And again, perfectly fine to do so because it has those d orbitals available to accommodate those. Any questions on that there? So along this time, we talked about the idea of, well, if you could kind of do the sort of expanded octet and you could go more than 8 and you can maybe come up with some different arrangements, you know, how do we know, you know, maybe if this Lewis structure is a good structure versus another one is a good structure. And one sort of aspect that we could use to help us determine perhaps to choose between different Lewis structures is one that's known as formal charge. And formal charge is basically the number of valence electrons in the free element minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. So number of non-bonding electrons minus 1/2 the number of bonding electrons. And we could use this to calculate the formal charge. So for example, if we look at something like SO4 2-, and we draw our Lewis structure again, 6 + 4 × 6 + 2 gives us 32. And if you just follow our normal sort of drawing Lewis structure, you will end up with a single bonded structure all the way around. And it's a good structure. But sometimes we do see it perhaps drawn where we do some double bonding action kind of happening. So, you know, is one structure better than the other? And again, we could use something like formal charge to help us decide that. For example, if we look at the oxygen, the single bonded here, the formal charge would be 6 - 6, which is our number of non-bonding electrons. So 1, 2, 3, 4, 5, 6, minus 1/2 our bonding, which is 2. That 6 - 6 is 0, minus 1 gives us a -1, which means all these oxygens are the same. They all would have a -1 formal charge. If we look at our sulfur in the middle, that's single bonded, that is 6 - 0 for non-bonding electrons, minus 1/2 of 2, 4, 6, 8. That gives us a +2 happening here in our sulfur. If we add up all of our formal charges, it does equal -2, which is good. Now, by putting our double bonds over here, if we do, again, our single bonded oxygen is going to come out the same. So it's going to be 6 - 6 minus 1/2 of 2, -1. Our double bonded oxygen now would be 6 - 4 for non-bonding electrons, minus 1/2 of 4. That is going to be 0. So this now has a 0 and a 0. And now our sulfur that has been double bonded up looks something like that. We now have 6 for the sulfur, 0 for the non-bonding electrons, minus 1/2 of 2, 4, 6, 8, 10, 12 gets us a 0. So technically speaking, if we use formal charge here, the guy on the right would be a better structure because we've done what is sometimes referred to as minimizing the formal charge. Remember, things with very large positive formal charges like +3s, 4s is not very plausible. Your best situation, if you kind of get the formal charge down to 0 and everybody kind of reduce the formal charge, is sort of your best overall situation. And remember that if you could get to 0, that's like a perfect sort of situation. And lastly, if you're kind of comparing formal charges, you would want the more negative formal charge to end up on the more electronegative atom, while obviously the more positive formal charge on the least electronegative atom. So we could use formal charge a lot just to straight out calculate what kind of the charge is on each of those elements in that bonding situation. But we could also use it to help us decide between different structures, which one would be a better structure versus something else. Any questions on formal charge there? This sort of led us into then sort of geometry. And in terms of geometry, we talked about certain types of geometry, but the simplest geometry that we talked about is our diatomic molecules. And those can be guys that basically only have two atoms. So you could have something like our F2, our H2, could be guys that are different, our HF, could be guys with double bonds, could be guys with triple bonds. It really doesn't matter if you only really have sort of two guys that are present. The geometry is always going to be linear no matter what, basically a straight line, right? The shortest distance between basically 2 points is a straight line. And that's sort of, what we would sort of have in this case. That then led us into sort of geometry of things where we have three or more atoms involved. And when we have three or more atoms involved, we oftentimes talk about geometry, which is sometimes referred to as VSEPR, the valence shell electron pair repulsion model, hence the abbreviation as we talked about. And in that situation, we really talk about kind of two types of names. One is the electron pair geometry, and one is the molecular geometry, or the shape. And really sort of the best way to sort of do it is to count, to sort of count up the number of electron pairs around the central atom. And remember, it's always the central atom that you're interested in, and really the number of bonds. There is a couple of things that you do want to keep in mind when you're doing geometry, and kind of only when you're doing geometry, is if you have a double bond or a triple bond, double or triple bond, it counts as one electron pair and one bond. So that's an important thing. It counts as really only one electron pair and one bond. So for example, if we had, something like this, here we have two electron pairs around the central atom and two bonds. Something with two electron pairs, the electron geometry name is linear. Again, that describes sort of the three-dimensional arrangement of the electrons around the central atom. And the molecular geometry is also going to be linear as well. If we move to something where we got something maybe like this, that if we count around, the X has three electron pairs and also three bonds. So something with three electron pairs is what is known as trigonal planar for the electron pair geometry. Again, it has that triangle 120 degrees sort of geometry or bond angle. Also going to be trigonal planar here for our molecular geometry. If we had something where, we had our central atom and four things attached. We have four electron pairs, four bonds. That's going to be our tetrahedral, and tetrahedral arrangement, again, going to be our 109-ish 0.5 degrees in terms of the bond angle. We also then got into a couple of our expanded octets, kind of, something with five things maybe attached. As five electron pairs and five bonds, that is going to be triangular bipyramidal. And the molecular geometry will also be triangular bipyramidal. And the last sort of expanded octet would be 6 and 6. So again, if we had something, obviously, kind of like what we just drew there with the SF6, kind of 6 things around it, if you will. That's going to be our octahedral and octahedral arrangement. So what we talked about and what we saw was that when we're in a situation, if we draw our Lewis structure and we have absolutely no dots on the central atom, so no non-bonding electrons, both of these names will be the same. So these guys are the same because they have all the way through here, no non-bonding electrons around the central atom. And the molecular geometry and the electron pair geometry will be the same. It's really, as we talked about, when we start introducing non-bonding electrons into the mix, that we do get a couple of things that happen in terms of the geometry of the molecules. First off, we have different electron interactions. There's electron interactions of bonding electrons near bonding electrons, which is what we have in these situations here. We now, when we get the non-bonding electrons in there, we could have bonding and bonding interactions. We could have non-bonding electrons and bonding interactions. And then we could have kind of the worst situation in terms of repulsion, because remember, the idea here is we're talking about electrons that are negatively charged, which means by the purpose of that, they don't want to be near each other, but they're stuck in a bond. So they try to escape each other. So when we get those non-bonding electrons and their non-bonding electrons, it's sort of the worst situation. And they really do try to get as far away as possible. What that affects is actually only one of the names. It actually affects the shape of the molecule or the molecular geometry sort of name. So this is the guy that is affected when we start to basically introduce non-bonding electrons around the central atom. So we talked about some of those. For example, we had something like perhaps this. And if we look at this 1, 2, 3 electron pairs, again, the double bond counts as 1 electron pair, and only 2 bonds. Double bond counts as 1 bond. The other guys counts as 1 bond. Again, because it still has 3 electron pairs, it's the exact same as the 3 electron pairs that we had up here. And that would give us our trigonal planar geometry. But now we have bonding electrons near bonding electrons, non-bonding electrons near bonding electrons. We're missing that extra atom in there with the bond. The geometry of this molecule changes to something known as angular, which is just under 120 degrees in terms of its bond angle. And again, it's because of that non-bonding electrons, the overall shape kind of flexes a little bit more. It's able to kind of spread out a little bit more, and we get this different geometry. We then, saw one like this, for example, 4 electron pairs around the central atom, but only 3 bonds. Again, 4 electron pairs means that the electron geometry is still tetrahedral. With the non-bonding electrons there, this guy makes that trigonal pyramid shape. Again, as we also talked about, not to be confused with the trigonal planar, right? So they are different, and you do have to identify planar or pyramid when you're doing one of those two, probably not at the same time. We also saw one where we had a couple of non-bonding electrons on the central atom. So that would be 4 electron pairs and only 2 bonds. Again, 4 electron pairs would be our tetrahedral. And with 2 bonds, this is a situation, as we talked about, that is sort of the worst, as it has all the interactions sort of happening. It has the bonding and bonding interactions, as the non-bonding and bonding electron interactions. And it also has the worst one, which is the non-bonding electrons near non-bonding electrons. Tries to get away as far as possible, and we get our bent, our V-shaped. A reminder that, sometimes people kind of use these names interchangeably, but there really is sort of a difference in terms of the bond angle. When we talk about something that's angular, it's hanging around the kind of 120-ish mark, a little less than that. When we're talking about something that's bent or V-shaped, we're talking about something in terms of the bond angle that's actually less than 100 and 104.5, I believe. Getting old, I forgot the bond angle there, but it's less than that. 109.5, I think, is what I'm trying to say. It's less than that, like 104 for like water, 107 for NH3. So there is a difference. So remember, in here we use bent or V shape for this situation. We use more of the angular for that situation there, where we have 3 and 2, because there really is sort of a difference in terms of the bond angles that we see in there. We also then had some of those expanded octets and those exceptions that we had, where we had 5 electron pairs, but only maybe 4 bonds. And that is, again, 5 electron pairs, which is our triangular bipyramidal. But this is our seesaw. We also had 5 electron pairs and 3 bonds. And that, again, is our triangular bipyramidal. And that would be our T-shaped, the guy that kind of looks like a T. And there's also 5 electron pairs and 2 bonds, which was triangular bipyramidal. And that actually gave us that linear sort of geometry. We also then had some of our 6 electron pairs and 5 bonds. That was our octahedral and our square pyramid, and our 6 electron pairs and 4 bonds, which was our octahedral and our square planar. So these were really the sort of the geometries. And again, what we see sort of on the bottom end here in terms of our list, these are guys that do have non-bonding electrons there. So all of these guys, we see different names when we look at the names here. And all these guys basically have different names because they do have non-bonding electrons sort of happening here. Any questions on that there? That also led us into a talk of, obviously, after doing the geometry, we did the formal charge. We also then talked about molecular polarity. So remember that molecular polarity is a little bit different than bond polarity that we talked about earlier, where we talked about bond polarity. We typically will use and sort of talk about it in terms of electronegativity values. So the only place where bond polarity and molecular polarity sort of cross over is when we're dealing with diatomic molecules. So when we talk about diatomic molecules, kind of bond polarity and molecular polarity are kind of the same. So when we talked about the HF earlier, we saw that that was a polar bond. And because that was a polar bond, and that's the only bond, it would mean that this is a polar molecule. When we have something like F2, as we also talked about earlier, that obviously they're going to be sharing the electrons equally. This is a non-polar bond. And again, because it's the only bond, the molecule would also be non-polar molecule. So really the only place kind of where bond polarity and molecular polarity are kind of the same thing is when you're dealing with really a diatomic molecule, because there's really one and only bond. There's only one bond present at all. And that's where we would sort of have those guys be the same. When we have 3 or more atoms, we do have to look at 2 things. You have to look at, is there polar bonds? And if there are polar bonds, you need to look at the molecular geometry of it. the shape. So for example, we talked about carbon dioxide, and it's a very good example because if we look at carbon dioxide, carbon and oxygen in the same period on the periodic table, oxygen more electronegative. So definitely here, it does have polar bonds. So you may be tempted to go, it is a polar molecule. But the geometry of this thing is 2 electron pairs and 2 bonds. This has a geometry that is linear, which means, as we talked about, the oxygen to the right is pulling, but we have the oxygen on the left pulling. So as they pull together, these sort of dipoles, which is what these arrows I drew, they basically cancel each other out. So these guys cancel in this situation. And the resulting is that this guy is a non-polar molecule because of that. And that is something different than when we deal with something like water, as we talked about. Again, also containing polar bonds between the hydrogen and the oxygen. And in this case, they actually add together to give us what is sometimes referred to as a net dipole moment. It's a very badly written moment. There you go, dipole moment. Heading in this direction, which means that this side of the molecule is more negative, this side is more positive. And that's because these are really vectors. So if we kind of, draw these vectors together, this guy's coming this way, this guy goes to sort of the tail of it, and they actually add together to head in this direction. And we get a net dipole moment that happens in this case. And this guy would be obviously a polar molecule. Again, polar molecules have dipole moments, and it makes them basically saying that as a whole, the entire molecule, there's a side of the molecule that's more negative, and there's a side that's more positive due to that as a whole in that molecule, unequal sharing of electrons. Now, we talked about, you could draw, you could try to visualize what's happening, but there is sort of a shortcut to figuring out molecular polarity. And as we talked about, pretty much if you draw your Lewis structure and you have one of those symmetrical geometries. So if you draw your Lewis structure and you got those symmetrical geometries, where basically you have no dots on the central atom and all the outside's the same, that typically would be a non-polar molecule. And typically speaking, if you draw your unsymmetrical geometries, and that's basically where you draw your Lewis structure and you do have dots on the central atom, and everything on the outside is the same atom. That typically would be a polar molecule. So for example, here, if we look at water, I see dots, I see everything on the outside is the same, polar molecule. If I look at this guy here, when I look at the Lewis structure, I see on the central atom, no dots. Everything on the outside is the same, going to be a non-polar molecule. Remember, though, that if you switch out one of those guys to something like a hydrogen, it will now become a polar molecule because we have we have polar bonds going this way. So 3 of those guys are pulling to the left. The hydrogen is not really pulling anywhere because it's non-polar, and it will end up being a polar molecule. There's actually 2 exceptions to those sort of symmetrical geometries where you do draw the Lewis structure and you do see dots. And the 2 exceptions is square planar and linear. In those cases, again, if you draw those guys and have those geometries, you will have dots, but because everything on the outside is the same and symmetrical in that sense, they actually will become non-polar molecules. So those are kind of the 2 exceptions in terms of molecular polarity where you could draw Lewis structure C dots and something be nonpolar. Question on that there. That then led us into everybody's favorite thing, which was hybridization. And hybridization, again, is sort of a bonding model to help us sort of describe sort of what is happening and why we see sort of some of the bond angles that we do see. So for example, hybridization is really where we take atomic orbitals, where we take some atomic orbitals like S, P, and D, and we basically mix them together through a hybridization process, which, as we talked about, involves electrons being promoted, some combination of these atomic orbitals into these hybrid orbitals. The idea behind hybrid orbitals is we create these hybrid orbitals, which are essentially the same shape. They essentially end up on the same energy level, creates for better bonding and the bond angles and stuff that we do see when we put it together. So hybridization is related to the electron pair geometry. So when we talk about the electron pair geometry, is related to our hybridization. And we do count up sort of the electron pairs the same way as we do geometry, which means if you come across a double bond or a triple bond, it still only counts as one. So the simplest one that you could have is, and you could count it off like this, there's two electron pairs, so perhaps 1 and 2, that is an S and a P, and that goes with our linear electron pair geometry. An S and two P's that come together, sp2, that is our trigonal planar. sp3 is tetrahedral. Then we do have some for our expanded octet sp3d, which is triangular bipyramidal. And our sp3d2, which is our octahedral. And again, what I drew there on the right is something that's very simply done and very easily used to help you identify hybridization of things. So for example, if we looked at CH4, we have 1, 2, 3, and 4. So you just start here at S always. So 1, 2, 3, and 4. That means that that carbon is sp3 hybridized. If you had NH3, remember, it doesn't matter if they're lines or dots. 1, 2, 3, and 4 also would be sp3. If you had something like, we did this carbon here, it has 1 electron pair. Again, triple bond only counts as 1 electron pair. So that's 2, 1 and 2 means that this guy here would be sp. This guy over here would also be sp in this particular case. If we looked at something like carbon dioxide here, 1, 2, and 3 electron pairs, 1, 2, 3 would be sp2. So we can really sort of assign hybridization pretty easily, counting electron pairs, again, using double bonds and triple bonds like we did before as only 1 electron pair. And again, it is related to the electron pair geometry name and not the, not the molecular geometry name. Any questions on hybridization there? With that, we talked about sort of, you know, some different types of bonding and how these bonds come together. So for example, when we make a single bond, typically that is what is sometimes referred to as a sigma bond. And that's basically the kind of head-to-head overlap that happens when orbitals come together straight at each other. And when we have a double bond, which is 2 lines, it's made up of a sigma bond, right, sigma, and a pi bond, And a pi bond is different. Pi bonds come from these unhybridized p orbitals. And it's a different type of overlap, is what is sometimes referred to as sideways overlap. And when we have a triple bond, which is 3 lines, we have a sigma bond and 2 pi bonds basically make it up. So when we look at something like this, we can look at this and we could count up the number of sigma bonds in this entire thing by really just looking for each line. So that's a sigma bond. That would be a sigma bond. That would be a sigma bond. One of these lines would be a sigma bond, and one of those lines would be a sigma bond. And that means that in this particular case, that would be, is that 5, I believe, in this particular case. Pi bonds would be made up of double bonds or triple bonds. So we would want to go and count up all those guys. So we would have obviously a pi bond there, and one more makes 2, and one there makes 3. So this guy would have 3 pi bonds. And again, we could do our hybridization. This carbon has 1 electron pair, 2 electron pairs, sp. This carbon has 1 electron pair on the left, 1 on the right, sp. This carbon here, 1 electron pair to the left, 1 to the right, 1 to the top, sp2. Remember, we could also, if we wanted to, apply hybridization to an outside atom sometimes. This oxygen has 1 electron pair, 2 electron pairs, 3 electron pairs. It would be sp2 as well. Any questions on hybridization, bonding, sigma bonds, pi bonds? Any questions on any of that stuff there? Okay, so that was bonding. We moved away from bonding at that point and sort of changed gears a little bit. And we started talking about really things like atomic mass. So the atomic mass is, again, when you look at the periodic table, that number there on the bottom. And the atomic mass is based on the carbon-12 isotope that we talked about. And remember that it is really the average atomic mass of all the naturally occurring isotopes for a particular element. And we could calculate the atomic mass by taking the percent abundance of the first isotope times the atomic mass of the first isotope, then add it to the percent abundance of the second isotope times the atomic mass of the second isotope, and then continue that pattern if you had 3 isotopes or 4 isotopes. And that would give you your average atomic mass in AMU, and that is usually the number that we see on the periodic table. You can do that by using some type of technique known as mass spectrometry to do that. And remember that also, for the most part, the atomic mass is how much AMU it is in an atom. And that is sort of numerically equal to a more useful value that we use most of the time, which is molar mass, which is in grams per mole. So your AMU that you see per atom on the periodic table is equivalent to being grams per mole on the periodic table. And grams per mole really is also, really what we see on the bottom here of the periodic table. We take that out, and that's how many grams there are per mole. And molar mass is really our conversion to go from grams to moles, or moles to grams, kind of back and forth, those two conversions. We could use that as a conversion factor. We could say that there's 12.01 grams per mole in carbon, and we could say 12.01 grams per mole up on top, or flip it around, moles per 12.01 grams. if you're going to do sort of a dimensional analysis sort of approach. We also could calculate the molar mass for something that's a molecule by really just adding up all the parts. So that would be 2 times 1.008 grams per mole from the periodic table plus 16 grams per mole gives us our 18.02 grams per mole, which obviously we could also kind of use as a conversion factor as well. Now, we also talked in this time about Avogadro and his number. So Avogadro's number really is our conversion factor to go from atoms or molecules to moles, or backwards from moles back to atoms or molecules. And remember that basically there is 6.022 times 10 to the 23. You know, again, this could be atoms, this could be molecules, the units could change, and 1 mole of something. And again, we use it as a conversion factor, really, 6.022 times 10 to the 23 atoms per mole, or a mole is 6.022 times 10 to the 23 atoms in this particular case. And we also talked about, at this point, percent composition by mass. So percent composition by mass. And basically what that means is if we had something like CH4, we would get the molar mass of it by adding up all the parts, 12.01 grams per mole plus 4 times 1.008 grams per mole. And if we do that in terms of the molar mass here, we will end up with 16.04 grams per mole. Percent composition by mass basically just means we want to figure out the percentage of carbon, and we would just take the mass of carbon that's present here, basically divided by the mass of the compound, times it by 100%, and we get 12.01 divided by the answer, and we'll call it 74.9% carbon. So mainly made up of carbon, this guy by mass. We do the same thing for hydrogen. There's 4 hydrogens at 1.008 divided by 1604 times 100%. And that gives us about 25.1% made up of hydrogen in this particular case. So we could calculate the percent composition by mass of these guys by basically taking the mass of each individual guy we're interested in and divided by the mass of the entire compound. This really led us into 2 different types of formulas, one being the empirical formula, one being the molecular formula, and how we calculate these guys. So let's talk a little bit about what those guys are. The empirical formula and the molecular formula. Remember that the empirical formula is the simplest whole number ratio of what's present, while the molecular formula tells us exactly how much is present of each element, basically. So if we have C2H4, that basically is 2 carbons to 4 hydrogens. That's the same as 1 carbon to 2 hydrogens. The empirical formula would be CH2 in this particular case. So one way, obviously, you could go from molecular formula to empirical formula is by simply reducing down everybody to the simplest whole numbers. Obviously, if you can't reduce down, they are the same. So like water, that again is 2 hydrogens for every 1 oxygen, You can't go any lower than that and still have whole numbers. So the empirical formula would be the same. We also talked about how you calculate the empirical formula. So the steps to calculate the empirical formula were some basic steps here. If you're given that sort of percent composition by mass, so if you have that percent composition by mass, you want to convert that into grams. You then want to convert those grams into moles of each element. You then want to divide by the smallest number of moles. And if you hit all whole numbers at that point, that would then be your empirical formula. Remember, though, that, if you divide and you don't hit whole numbers, so for example, if we converted and got 6 moles of A and 2 moles of B, we would divide by 2 in each of these cases, gives us 3A and 1B. That would be an empirical formula A3B. If we had 5 moles of A and 2 moles of B, and we divided by 2, we would end up with 2.5 A and 1 B. That isn't too far to round, remember, so you need to multiply by a common number. If you did 2.5 times 2, that's going to be 5, right? So if you went 2.5 times 1 is 2.5, 2.5 times 2 is 5. So if we multiply my bad empirical formula by 2 here, basically, this factor, that would give me the proper empirical formula of A5B2. So remember that when you're doing sort of a textbook problem and you're trying to calculate the empirical formula, really it needs to be super close in order for you to round, like a 0.998, 999, 97, or just over the number, like, 1.03 or something like that. That's close enough to round. But when you typically get those numbers, like we talked about, where you get like a 0.33 or a 0.25 or a 0.5, those are too far to round. So you do need to find that factor by which to multiply the empirical formula by to get yourself to the proper empirical formula. We also talked about how to do the molecular formula. So to calculate the molecular formula, remember, you pretty much need 3 pieces of information to get yourself to the molecular formula. You first need the empirical formula, and it may be given to you, or you may have to calculate it. Once you have the empirical formula, you need the molar mass of the empirical formula. And again, you may have to calculate that yourself usually. And the third thing is the molar mass of the compound. And again, in textbook problems and most problems, that number is usually given to you. So somewhere along the way, they'll say, hey, the apparent molar mass is 100, or they may even give you a range, remember, but they'll give you some type of value for what the molar mass of the compound typically is. And what you do with that is you take the molar mass of the compound and you divide it by the molar mass of the empirical formula. And that's going to give you a number. And in this case, you could round this number. In this only case, you could do that. And again, let's just say, for example, that this was my empirical formula here. And I did this and I got a 3 when I did it. What that means is I would take my empirical formula and multiply everybody by 3, and that would give me A9B3 would be my molecular formula. So again, sometimes the empirical formula would be given to you, or sometimes you do need to calculate it. We also talked about as well that you can go in this approach, which is a pretty safe approach, do the empirical formula to the molecular formula, but we also did a couple examples where we worked it backwards, where you start with basically the molecular formula and the percent composition and kind of work your way back to the empirical formula. And you could do it that way as well. Any questions on grams, moles, Avogadro's number, empirical formula, molecular formula? All right, then clearly the next major topic that we talked about is nomenclature. And nomenclature obviously is naming. So we really broke up nomenclature like we kind of broke up for the most part our bonding. And first off, we talked about ionic compounds, which obviously are metals and non-metals. And we had basically in a formula of an ionic compound, it's always the cation first, the positive guy, followed by the anion. And remember, when we put these guys together in a formula, we always want to make sure that the overall charge is 0. And what that means is we need to balance out the positive and negative charges in the simplest way that gets us to 0. So again, for example, if we had an iron 2, we would need 1 and 2 of these guys to come together to give us iron 2 chloride over here. The proper formula for an ionic compound, no charge. If you were asked to write the cation, should have a charge, or if you're asked to write the anion formula, should have a charge, but the formula together does not. We had type 1 compounds, which are ionic compounds. They are a metal and a non-metal together. And the most important thing always when you have a metal and non-metal together, or metal involved, is the metal. And in a type 1, that is group 1, 2, 3. That is silver, cadmium, or zinc. And what these all have in common is they all have fixed charges. Remember that silver is +1, cadmium and zinc is +2. Those are 3 exceptions in the transition metal region, that even though they're transition metals, they still only have 1 fixed charge. When we name these guys, we simply just use the whole name of the metal. The non-metal gets the IDE at the end of it. So when we take NaCl, that is sodium chloride, as sodium is group 1. And that's really as far as you need to worry about, because that means it's type 1, whole name of the metal, IDE on the non-metal. Remember that even if there's a number on that non-metal, we don't use the number, we don't use a prefix. It's just simply the non-metal name with the IDE at the end of it. Type 2 compounds are our metals and non-metals as well. Again, the metal being important here, the metal is a transition metal. Are just to write on the periodic table. Remember that those guys have basically a variable charge, which means in certain cases, the same element could be +2 or +3. So because of that, when we name it, we still kind of name it the same way, whole name of the metal. The non-metal, again, gets the IDE at the end, but we add a Roman numeral here. And the Roman numeral is the positive charge on one metal. So if we come up here to our FeCl2, Fe is a transition metal. Not sure what the charge may be, but we do know Cl is -1, and there's 2 of them, gives us a -2, and that's how we know it is iron with a +2, which means the name here would be iron Roman numeral 2, and again chloride. Even though there's 2 of them here, no prefix, positive charge is what the Roman numeral is for. Question on those 2 types of naming. We then talked about type 3 compounds. Type 3 compounds are a different type of compound. Type 3 deals with The exceptions for the ones that don't need Roman numerals would be really these three guys right here. So these are the transition metals that have fixed charges. So that's why when we have something like AgCl, we call this just silver chloride. Even though silver is +1 here and is a transition metal, it is a fixed charge of +1, so it does not need a Roman numeral. And cadmium or zinc as well. Lead does need a Roman numeral. Again, lead would need a Roman numeral. And remember that it's the transition metals. So for our type 2 over here, for our type 2, it really is the transition metals. But where that staircase comes down, it's also these guys over here where we have lead, we have tin, we have bismuth, and so forth. Those guys are named as type 2 as well and do need a Roman numeral. Yeah, so I think I just got your question. I hope so. One more time, the guys just to the right of the transition metal, but below the staircase. So if we look at a periodic table where lead is, tin, antimony, bismuth, those guys in that region need the Roman numerals. Other questions on that? So then we went into type 3, and type 3 compounds are covalent compounds. So these are our guys that are really sharing of electrons, and these are really between two nonmetals. And because we have sharing of electrons, these are actually the ones where we do use prefixes. So these are actually the ones where we actually use the prefixes. So that's mono, which obviously means 1, di, which means 2, tri, which means 3, tetra means 4, penta means 5, hexa means 6, and so forth. Now, there's a couple of rules. We do not use mono on the first name, but it's okay on the second. And we do get a couple of places where we get a couple of vowels together, where we typically will drop off the vowel on the prefix, so we don't get some weird things. So if we have N2O3, this would be dinitrogen, and we use the whole name here on the first element, and trioxide, and on the second element we use the appropriate prefix and the nonmetal with the IDE at the end of it. And again, these are the easiest ones to sort of name, but really the ones where people kind of screw it up the most by trying to do some weird things. Remember, we never mix those things, prefixes, Roman numerals, or anything like that. Everybody has basically their own spot. We then talked about as well in terms of naming our polyatomic ions. And again, those are our guys like NO3 minus, NO2 minus, this being nitrate, this being nitrite. Remember that sort of in a group of two that are related to each other, the one that has the more oxygens ends in 8. The one with the least number of oxygens ends with ite. Sometimes we do put an H in front of something, and that becomes something like hydrogen carbonate or bicarbonate. Yeah, to answer your question, no type 3 guys should have mono in the front. You shouldn't use mono on the first name at all. So just to go back for a second here, if you had something like CO, like we talked about, we don't use mono on that first one. We just simply use the name of the element, no prefix. It's assumed that there's no prefix, it just means one, but we would use it on the second name. So this would be carbon monoxide. So mono, never used on the first name. So this is hydrogen carbonate or bicarbonate, sometimes called. Remember, there's also a group of fours. They're sometimes related to each other. And again, you could kind of follow the same approach, break them up by least oxygen this way, and we get chlorite. The one with the least number of oxygen in a group of four starts with hypo and ends with ite. This guy would be chlorate, and the one with the most oxygen in a group of four starts with the per in front of it. And remember that you could really swap out any of those guys for a halogen. You would have like bromate, bromite, in there as well. The only kind of positive polyatomic ion is ammonium. There are some that do end in IDE, like hydroxide. But remember that for the most part, these polyatomic ions will really be hooked up with metals. So we follow kind of the type 1 or type 2 rules with them. So NaNO3 would be sodium. And we just use the full name of the polyatomic ion. So that would be nitrate. And remember that if we have more than one polyatomic ion, we do need to put parentheses on how many there are on the outside. And this would be copper Roman numeral 2. And again, even though we have two of the hydroxides, it would still just be hydroxide. So for the most part, these polyatomic ions, as we talked about, pretty much going to be hooked up with a metal. And really, again, you want to default back to the metal sort of rules. If it needs a Roman numeral, you need to put it. If it doesn't, you don't. And I think the last thing we talked about in terms of naming was how to name acids. Remember that acids are really substances that are able to produce H plus in solution. And basically, when we talk about acids and how to name it, it's all about oxygen and whether or not there's oxygen present. So if the answer is no oxygen, then basically it would start with hydro something ic acid. So like HCl would be hydrochloric acid. Remember, we do put the aqueous symbol next to it to indicate that it's an acid, and that's the distinction between that and this, which would be hydrogen chloride gas. Yeah. So the aqueous symbol means it's an acid and it's hydrochloric acid. The gas obviously would mean it's not an acid in that case. If it does have oxygen, it will have one of those polyatomic ions, which obviously ends in ate or ite in most cases. And if your polyatomic ion ends in ate, your acid will be something ic acid like HNO3. NO3 is nitrate, which means this would be nitric acid. If your polyatomic ion ends in ite, it will be something OUS acid like HNO2. NO2 minus is nitrite. This would be nitrous acid. So remember, it's all about oxygen when we name acids and whether it has it. If it does not have it, then those are the only ones that have hydro. Guys that with oxygen do not have hydro in the name. The last thing that we talked about names were some common names that we just use, like H2O is water, NH3 is ammonia, and CH4 is methane. Any questions on that there? Any questions on naming? Because I think that wraps up naming there. All right. Okay, so we're going to continue on here. So we just sort of finished up talking about nomenclature. So after we kind of went back to nomenclature in that chapter, which I think was chapter 3, we then started to roll into sort of the next big topics, which is sort of equations and doing calculations and stoichiometry from equations. So from there, we went to balancing equations. And remember that obviously when we balance equations, as we talked about, we only change the coefficients. And the goal obviously is to end up with the same number of elements on both sides of the equation. So, if we had something sort of like this here, remember we talked about sometimes it's easy to sort of make a table of what you got on the reactant side, product side. So here we would have 2 and 1. We would have 2 and 3. Start with maybe what's the easiest. We would put a 2 in front of there. That gives us 2 nitrogen, gives us 6 hydrogens, allows us to then come over here and put a 3 in front of there. 2 nitrogens and 6 hydrogens. This again would represent the balanced chemical equation. Other things that we talked about here, 2 main things that you want to remember is to have a properly balanced equation. All need to be whole number coefficients. And it does need to be the simplest set of whole numbers. So remember again that if you were to balance an equation like this, you could definitely go through and reduce all these down by 2 and end up with this equation here, which would be the properly balanced equation. And again, sometimes that happens because people could see larger numbers as they're balancing. You just want to double check that you have all whole numbers, and if you can, go back through and reduce everybody down and get everybody still a whole number. You should do that to have really the properly balanced equation. Other things that we talked about is if you have a bunch of polyatomic ions in there, sometimes it's easier to balance those polyatomic ions as kind of whole units rather than individual elements. And lastly, although in the end, when you do properly balance your equation, it all needs to be whole numbers. You can definitely use a fraction to help yourself balance it. Just you have to clear the fraction to have, again, that properly balanced equation. Once we talked about equations, we kind of rolled into different ways to classify equations. And really, ultimately, there's really kind of 2 big categories of equations that we talked about. One big category was double displacement reactions. And really the other big category was redox reactions that we talked about. And remember, when we talk about a chemical reaction, there's really kind of 3 main driving forces for a reaction to occur. One is an electron transfer. One is the formation of a solid or a precipitate. And one is really the formation of water. And these are really sort of, what drives a reaction to take place, why a reaction takes place, really the main reaction that does take place when we do see chemical reactions. We also talked about the idea that you could definitely sort of classify the same reaction in multiple ways depending on what you're looking at. So under sort of the double displacement sort of banner of reactions, where in general, the double displacement reaction is, again, A and B, C and D. And as we talked about, the way you recognize these guys is really you got 2 ionic compounds happening, a positive negative guy and a positive negative guy. And really the 2 positive cations basically switch partners. And we end up with 2 new ionic compounds on the product side. And in certain cases, these products could be soluble, which means it's aqueous. And in other cases, you may get something that's insoluble, which means you get a solid that's formed. What determines sort of whether or not we kind of get a solid or no solid in these reactions, we can use our solubility rules that we talked about to help us decide, would we get a solid or not? These are things, if you remember, things like nitrates are soluble in everything. Things like chlorides or bromides or iodides, they're soluble in everything. But there are some exceptions like silver, lead, and mercury. And again, if it's an exception, it would be opposite of that, and it would make a solid or be insoluble. Obviously, there's a bunch of rules that you could reference, but we do use these solubility rules to help us decide, whether or not we would expect, if we put these two ions together to make an ionic compound, would we expect a solid to form or not? And one of those driving forces is a precipitation that is made. And that's another way that we could classify sort of a double displacement reaction as a precipitation reaction, which is really just a double displacement reaction that results in a solid being formed. So if we took something like we've seen before, silver nitrate, which based on solubility rules would be soluble, along with something like sodium chloride, which again, sodium is soluble in everything. Again, we have a positive, negative, positive, negative. Silver will then hook up with our chloride here, and that will make a solid based on solubility rules, and our sodium and nitrate will come together and we'll make something that's aqueous or a solution, again, two new ionic compounds on the other side. We also talked about this as this is the molecular equation. We can write another equation that more adequately describes what is going on in this situation by breaking up everything that is a strong electrolyte and anything that's a weak electrolyte, anything that's a solid, liquid, or gas stays together. So silver nitrate would break apart again into silver plus some nitrate plus some sodium plus some chloride. Again, the silver chloride, which is a solid, will stay together, and our sodium and our nitrate will break apart. This is what is referred to as the total ionic equation, or a complete ionic equation. And remember, in this equation, we could find ions on both sides that look exactly the same. And in this case, the sodium and the nitrate looks exactly the same on both sides. These are what are referred to as spectator ions. They're really just hanging out there and watching what's going on. We typically cancel those out. And that leaves us our third type of equation that we talked about, which is our net ionic equation. And that's pretty much what's left over, which is our silver ion in this case goes and finds the chloride ion that's floating around in the solution. They come together to make that silver chloride, which again is a precipitate, which is why it's called a precipitation reaction and why it's a driving force for this reaction to take place. And that is what is known as a net ionic equation. Any questions on those? A reminder that when we write net ionic equations, because they are ionic equations, there should be charges associated with everything that is ions when you do write these type of equations. So double displacement reaction, a precipitation reaction, they're really the same thing in this case. Two different ways to classify it, but again, we classify it as a precipitation reaction because a precipitate was made. Another sort of type of reaction that we could classify that falls under that double displacement reaction was the acid-base neutralization reaction. And remember, when we take an acid plus a base, we basically make two things. We make a salt and water. The water really comes from the H plus from the acid, and the OH minus from the base is basically where the water comes from. The salt is basically an ionic compound, whatever is left over. And remember that whenever we take a strong acid like hydrochloric acid plus sodium hydroxide, which is a strong base, again, it really is a double displacement reaction. H plus from the acid, OH minus from the base. That is where we make our water. Sodium +1, chloride -1, sodium chloride here, which would be our salt, so our water in this case. And again, whenever you do a net ionic equation or a total ionic equation with a reaction of a strong acid and a strong base, it always ends up in the exact same place when it's all said and done. Here we see, in this case, the sodium and the chloride are spectator ions. They cancel out, and this is the overall reaction that you always get when you react a strong acid with a strong base, is basically the H plus from the acid goes and finds the OH minus from the base, and they make water, which again is another driving force for a chemical reaction to be made, is the formation basically of water. So underneath sort of the double displacement reactions, as we talked about, are precipitation reactions, which are really double displacement reactions that make a solid, acid base reactions that make a solid. And we also talked about double displacement reactions that can produce gases. So if you remember, if you take something like hydrochloric acid plus some sodium carbonate, you will get some carbonic acid plus some sodium chloride. That carbonic acid then will go through a decomposition reaction, produce H2O and some CO2 gas. So the third thing we talked about in terms of double displacement reactions is there's sometimes double displacement reactions that will generate a gas directly. And there's a lot of times double displacement reactions that will be followed by a decomposition reaction and produce a gas as sort of a secondary reaction, as the case over here where CO2 would be produced. Any questions on double displacement reactions? That left us pretty much the rest of the umbrella being really redox reactions. And redox reactions are oxidation and reduction reactions. And remember, you could do the oxidation is losing electrons. Reduction is gaining electrons. People again go with the oil rig, or Leo the lion goes grr. Don't forget though that we also talked about oxidizing agents. And reducing agents. And remember that the thing that is the oxidizing agent is actually getting reduced itself. And the thing that's the reducing agent is the thing that is getting oxidized itself. Remember, they're called the agents because they cause that effect in the opposite species. Sometimes people find it hard to figure out what's going on in terms of what's being oxidized and reduced, and we could do our oxidation numbers to help us with that. Remember, oxygen's -2, and you can assign your oxidation numbers. And you can use a simple number line approach to figure out what is being oxidized, what is being reduced. If you're being oxidized, you're becoming more positive. So if you see the oxidation number move in this direction, that substance is going through oxidation. When you gain electrons, you become more negative. So if you see somebody moving in that direction in terms of their oxidation number, that is something that is going through reduction. And sort of under the big classification of redox, it's really a transfer of electrons, which is that driving force. We have types of reactions like single replacement reactions. And that is where we have A plus BC. And again, this could be a metal or non-metal. And again, if it's a metal, it will replace out the positive guy in the ionic compound and make a new ionic compound. And this guy will come out with no oxidation state. Like, for example, here, if we take zinc plus our hydrochloric acid, zinc has a 0 oxidation state. This has a +1. This has a -1. Zinc will come in and kick out the hydrogen and make zinc chloride. Plus the hydrogen gas will come out. And this is now +2 and 0 and 0. And again, what's happening is really, if we look at it, the zinc is going from 0 charge and losing 2 electrons to become a +2 charge. And it is going through oxidation, again, starting at 0, ending at +2, going in this direction, oxidation. It's actually the hydrogen here. I guess I should balance it, put a 2 there. The hydrogen here is actually gaining a couple of electrons and becoming H2, which has no oxidation state or 0. So hydrogen is actually starting at +1 and ending at 0, which means it's moving in this direction and going through reduction. This is our oxidation half reaction. This would be our reduction half reaction. And in this particular case, the zinc would be our reducing agent. And the H plus here would be our oxidizing agent in that particular case. But this is, again, a single replacement reaction, which is really a redox reaction that's happening here. And again, we saw the halogens that could come in there and replace it as well. We could add these together and get our net ionic equation that's happening here, which is really the zinc plus a couple of these guys. Go to the other side to make our zinc plus this guy here. And that, again, would be our net ionic equation happening over here at the bottom. Any questions on that one there? We also talked about, speaking of sort of redox and those type of things, we talked about balancing redox reactions, more complicated redox reactions in acidic and basic solution. And sort of a simple redox reaction like we just did there, the main thing that you want to make sure is that you have the same number of electrons on both sides of the half reactions. Here, in a more complicated redox in acidic or basic conditions, there were several steps that we followed, and they basically were, you want to make sure you split off your half reactions. You want to balance with coefficients. Everything but oxygen and hydrogen. So just like normal, put a number in front if it's some like 2 chromiums on one side versus the other. Then what you want to do is you want to balance that oxygen by adding water to the side that needs the oxygen. Then add 2H pluses to the other side for every hydrogen water that you added. Because remember, when we add the water to one side to balance out the oxygen, we're also adding hydrogen as well. So we don't end up with the wrong number of hydrogens. We do need to add the H plus to the other side. Once you do that, you could add electrons to balance the charge in each half reaction. Remember, the charge does not have to equal 0 in each half reaction. It just needs to equal the exact same charge on each side, exact same number. And remember, by identifying what is being oxidized, what is being reduced, you'll know which side you should be adding the electrons. If it's an oxidation half reaction, electrons should be added to the product side. If it's a reduction half reaction, the electrons should be added to the reactant side. Once you bound it together, you got your electrons added, you want to make sure you have the same number of electrons in each half reaction. And if you don't, again, you need to multiply maybe one half reaction or both half reactions by a number. Once you got both of them with the same number of electrons, you want to add the reactions together. The electrons should cancel completely. And that would give you your balanced redox reaction in acidic conditions. Remember that if it is basic conditions, the easiest way to approach it is to basically do everything like you just did there in acidic. So balance it in acidic conditions. Then at the end, you will have some H plus. So you want to add an equal number of OH minus to both sides. And the side that has the H plus and OH minus together, you want to combine to make water. And then you usually have to reduce down the water. And what you're left with at the end of all that is your balanced equation in basic conditions. So we did a lot of work on that. We did a whole lab on that, a couple of labs, I think. And again, it will tell you to balance it in acidic conditions or tell you to balance it in basic conditions. Remember that you kind of know when you're done with these, you want to make sure that you have done basically two things. It needs to be balanced when it's all said and done. It needs to be balanced, right up here, I think, with the same number of elements on both sides. So just like a normal equation, you should have like 2 chromiums on the left, 2 on the right. And the charge on the left of the arrow needs to equal the charge on the right-hand side of the arrow. So when you add up all the charge on the left-hand side, it does need to equal the exact same charge on the right-hand side. Again, it doesn't have to equal 0, but it does need to be the same number on both sides. Any questions on redox reactions there? Now, in addition to single replacement reactions, there's some other classifications of reactions that are also redox reactions. And that's the rest of the ones that we're normally probably familiar with. That's our synthesis and combination reaction. And again, that's basically when we put two things together. So A plus B makes AB, like sodium plus some chlorine, makes some sodium chloride. Again, oxidation number 0, 0 plus 1 minus 1, sodium being oxidized, chlorine being reduced. We have a decomposition reaction, which is the opposite of that reaction. That's when we take one thing and basically break it apart into a couple of things. So if we took water into hydrogen gas and oxygen gas, 0, 0 plus 1 minus 2, oxygen is going from -2 to 0 being oxidized, hydrogen going from +1 to 0 being reduced. Redox reaction, also again a decomposition reaction. A combustion reaction, and remember there's sort of a really generic definition of a combustion reaction, which is pretty much you have some oxygen involved, is their basic definition. So even this reaction here, which we could also classify as a synthesis or combination reaction, and also a redox reaction that's happening, it could still be classified as a combustion reaction. Although most people probably would look at this and call it a combination or synthesis reaction, still meets the criteria for combustion because there's oxygen. Most people, when they think about combustion reaction, think about that organic combustion reaction that we talked about. And that organic combustion reaction involves an organic compound that usually is carbon, hydrogen, or oxygen there, like CH4, for example, plus some O2, makes some CO2 plus some water. So that's more so, I would say, probably if you mention, hey, what is a combustion reaction to somebody, probably 9 times out of 10, that's probably what they're going to tell you and talk about. But again, this is just really a generic definition or general definition of combustion that meets that sort of criteria. So all of these guys here are pretty much, especially the guy on the left there, you know, they're redox reactions in the sort of the big classification. Again, you can get more specific and classify the same reaction a number of ways. As we could see here, this one particular reaction here, we could actually classify 3 different ways. We could call it a combustion reaction. We could call it a synthesis reaction. We could also call it just a redox reaction as well. So you definitely can classify reactions in multiple ways, just sort of what you're looking at as to, you know, which way you might want to classify a reaction. Any questions on types of reactions there? All right, then we sort of moved into talking about calculations involving reactions. That's also known as stoichiometry. And remember, stoichiometry is really always based off of a balanced equation. And when we do stoichiometry problems, we use what is referred to as the mole-to-mole relationship. So from an equation like this, we could say there's 2 moles of A for every 3 moles of B. For every 2 moles of A you throw in there, you get 3 moles of C out. Every 3 moles of B, you get 3 moles of C out. And remember, for each of these, we can write really 2 conversion factors, which is really what stoichiometry is. It's really nothing more than sort of a conversion factor. We use stoichiometry to try to answer questions like how much product we may produce in a reaction, or if we produce a certain amount of product in a reaction, how much reactant maybe we started with. And in a basic stoichiometry problem, there's really 4 steps. Always starts with a balanced equation. So whenever you're given an equation, you do want to take a second, make sure it's balanced, especially if you don't see any coefficients. You want to take a second to make sure. You want to convert whatever they gave you into moles. And again, this could be grams to moles. This could be volume and molarity to moles. This could be ideal gas law to moles, you know, a lot of different ways to get there, but you want to convert whatever they gave you into moles. You then want to use that mole to mole relationship to go from what they gave you to what you're interested in. And lastly, convert those moles into other units. And, you know, so for example, here, if we started with, say, 10 moles of A in my example, and we want to know how many moles of C we would produce, we would start with the 10 moles of A. Again, going to the equation, we see A and C's relationship right there. And we would do our 2 moles of A for every 3 moles of C. That's going to give me 30 divided by 2, which is 15 moles of C. We then, if we knew what C was, molar mass, we could convert that to grams if we needed to. This is what is referred to when we do this calculation from the actual equation. This is what is referred to usually as the theoretical yield. Yield has to be a product. So whenever you solve for a product, it is basically what is referred to as a yield, a theoretical yield if it comes from the equation. Also a reminder, in stoichiometry problems, we could do relationships where we go from right-hand side to the left-hand side of the arrow. We could go across the arrow. We could do relationships between these two guys. If there was another product, we could do relationships between those guys. So you don't necessarily have to go across the arrow when you're doing stoichiometry. You could really answer information about everybody. Any questions on the basic stoichiometry problem there? Then we got into obviously limiting reagents or limiting reactants, and limiting reagents is the idea that whenever you do a reaction, there's always going to be one reactant or reagent that gets used up first. And the problem with that is what is known as the limiting reagent, I guess I should say that. There will also be really some reagents that you will have left over, and that is what is known as the excess reagent. And remember that it is always the limiting reagent that is the most important, because pretty much once that guy is gone, there is no way that you can make more product. So it is always the limiting reagent that determines how much product you make. How do we know we have a limiting reagent problem and it's not a basic stoichiometry problem? The way that you know that is you're given enough information to calculate the moles of all the reactants. So whatever that information may be, and it may not always be grams, maybe some other information, but if you see that, hey, I have enough information to calculate the moles of each of the reactants, then I know it's a limiting reagent problem, which means there's different ways you could do it that we talked about, but you do at some point need to determine which one is your limiting reagent. So for example, one way that we talked about, which is sort of a nice way of doing it, is by doing sort of a nice table. So if we have, say, this equation here, I'll just make it up here. We could do a nice table where initially we could put the moles in. And again, I'm just making up these numbers, obviously. 2 moles of this guy and 0 of this guy. The change part is the important part when you do a nice table, because that takes in the mole-to-mole relationship. So the 2 here is where the 2 comes from. It's minus because we're assuming that the reactant should be decreasing with time, and this would be minus 3x, while the product should be increasing with time. So that would be plus 4x. And it's really important to have those numbers there, which come right there from the balance equation, because that essentially does the mole-to-mole relationship for you. If you don't put those numbers in there, you're not doing the proper mole-to-mole relationship. You will not get the right answer. When you do sort of the ice table approach, what you then do is basically just carry everything down, and you get 4 minus 2x, 2 minus 3x, and 4x. Now, at this point, what we need to do is figure out which one is our limiting reagent. We're going to set each of these equal to 0, basically, the reactants only, and solve for x. And when we do that, if we do that, we end up with 4 is equal to 2x, x is equal to 2 in this example. Here we end up with 2 is equal to 3x, and x in this case would be 2 divided by 3.67. So what are we looking for when we do this in the ice table? Well, we are looking for the smallest number. And because this is the smallest x value, that tells us this guy is the limiting reagent, which means in my made up example here, this would be the limiting reagent. This would be the excess reagent. Again, the nice thing about this is actually then 0.67 moles. And it is every x value that we see here in the table, which means if we want to know how much product we produce, we know that the moles of C is equal to 4 times x, which in my example would be 4 times 0.67 moles. And that would tell us that we would produce, in this case, 0.67 times 4, 2.68, looks like, moles. 2.68 moles of C would be produced. That would be our theoretical yield. And if we want to figure out how much of our excess reagent was left over, we could simply go back to our excess reagent, which in our example here was A, I believe. And we see that it is equal to 4 minus 2x, which means 4 minus 2 times 0.67 moles. And again, we could very quickly figure out how much of our excess reagent was left over, which in this case would be 2.66 moles of A was left over. So this is a very convenient way of figuring out how much you would produce. It's a convenient way of figuring out how much of your excess reagent would be left over. Clearly, if I knew what the molar mass of all these things were, I then could figure out how many grams were left over. Question on the ice table approach to limiting reagents. Other sort of popular methods, as we talked about, is taking each reactant individually, figuring out how much product each one makes individually. And again, the one that produces the lowest amount of product would also be your limiting reagent and your theoretical yield. So that's another very popular way people do sort of limiting reagent problems. We put this together with our theoretical yield and talked about percent yield. And our percent yield is our actual yield divided by our theoretical yield times 100%. Remember that usually in a problem, the actual yield is given to you. You oftentimes have to calculate the theoretical yield. That's the one that comes from the actual formula and stoichiometry calculation. Remember that when you do percent yield, it's actually high numbers what you're looking for, but also a reminder that super high number over 100% usually means something went wrong. So, you know, a high number is what you're looking for percent yield, but not, again, over 100%. This rolled us into some talk of solutions and concentrations. So solutions really made up of two parts. It is made up of the solute and the solvent. And, you know, NaCl, that aqueous usually indicates it's a solution. And really what a solution usually means is you took something that's solid, for example, and dissolved it in a solvent like water to make a solution. If you ever need to know what the solute is usually the name of the solution. So obviously if I have a sodium chloride solution, the solute is sodium chloride. We talked about some percent concentrations. We had percent mass to mass, and that is the mass of the solute divided by the mass of the solution times 100%. Remember, in this case, the mass of the solution is both of these guys. So you want to make sure you have both of those guys added together, as it is oftentimes given separate in these problems. Percent mass to volume is mass of solute over volume of solution times 100%. And percent mass, percent volume to volume is the volume of solute over the volume of solution times 100%. Remember that if you do have like a 4.5% mass to mass solution of sodium chloride, that does mean you can convert it into a conversion factor. 4.5 grams of sodium chloride and 100 grams of solution are in 100 grams of solution 4.50 grams of sodium chloride. So you can use that as sort of a conversion factor. Now, the most common unit of solutions in terms of concentrations is really molarity, and that's obviously the one that we use the most. Molarity, as we know, hopefully is moles of solute per liter of solution. And you could think of that as moles per liter. And we could rearrange this. Liters would be moles divided by molarity. are the one that we use a lot. Moles is equal to liters times molarity. Remember that if you're doing something like this, the volume does need to be in liters to properly cancel out, and not milliliters, because you won't get moles. You will get millimoles, as we talked about. We also talked about dilutions with solutions. And that's where we could use M1 V1 equals M2 V2, or a more generic one, C1 V1 equals C2 V2. Molarity volume kind of before the dilution. And this is after the dilution, are the more concentrated solution and the less concentrated. Remember that usually when we do a dilution, the only thing that changes is the solvent. So the moles of solute before will equal the moles of solute after you do the dilution. And that's why we do see the molarity go down, because when we add more solvent, we are only changing this number. This number is getting bigger, which means that our molarity will go down when we do a dilution. Any questions on that there? We also talked about a couple of other sort of concentration type things. We had our mole fraction. And remember, our mole fraction is the X, and basically is the moles of interested in divided by the total moles. It really is kind of like a percentage without the multiplying by 100. So you get like a point something number. We also had little m, which is molality. And that is moles of solute per kilograms of solvent. So that's a unit that we saw with colligative properties later on as well, that's used there. We also talked about titrations, which are really solution stoichiometry problems. And really the only difference that we do is, we kind of use this version of molarity to get the moles. And a lot of times we will then maybe calculate the molarity at the end. We may calculate a volume at the end in these type of problems. So there's a few different sort of places. But remember, a titration is really where we use something like a burette, and we add, say, something like sodium hydroxide, a known solution, to like an unknown solution, like an acid. And remember that we titrate here, we put an indicator in, and really, we go until we reach what is referred to as the equivalence point. And in an acid-base titration, the equivalence point is where the moles of the acid will equal the moles of the base. And we did a lot of sort of calculations involving this, including a big experiment sort of calculations. And it really is a stoichiometry problem where we really just sort of do the same 4 steps usually. You want to make sure, again, you have that balanced equation when you're doing a titration problem. We want to convert to moles. And this is really a lot of times a solution stoichiometry where instead of grams to moles, we do use that liters times the molarity, right? So that those guys cancel out and you end up with moles, right? That's molarity right there. So that's the main difference. The third step is really the same. It's the mole to mole relationship from the balanced equation. And the fourth step also varies. We go from moles to some other unit. And a lot of times in, like I said before, sort of stoichiometry problems or titration problems, we will have moles at this point. So we may solve for molarity by using those moles to get to molarity. We may also, since we have moles at that point, we may also have the molarity again at that point, and we may divide by the molarity to get the liters. So, at the end of a titration problem, these are 2 very common sort of calculations that we typically do. So, for example, H2SO4 plus some sodium hydroxide, giving you some sodium sulfate and some water. And again, if we started with 20 milliliters of this guy and we use a titration that required 10 milliliters of 0.1 molar sodium hydroxide, from this information we could get moles. So we would convert our volume into liters. We would times it by the molarity of our sodium hydroxide. That would get us our moles of sodium hydroxide, as the liters would cancel. We then could do our mole to mole relationship from the balanced equation, and we would have 2 moles of sodium hydroxide, 1 mole of sulfuric acid. That's the big stoichiometry part. That then gets us to moles of our sulfuric acid. We then have the volume of sulfuric acid, which also needs to be converted into liters. And now we could get to the molarity of our sodium, of our sulfuric acid. Again, basic steps: 1, convert to moles, mole to mole relationship, convert to what you need. Again, the same basic 4 steps in a regular stoichiometry problem. But again, just sort of different ways that we get to moles using volume and molarity. And at the back end, instead of taking moles and the molar mass to get the grams, we oftentimes will use molarity on the back end as well. Question on titration, solutions, stoichiometry. Any questions on any of that stuff there? Then we rolled into big chapter on gases, where we saw a bunch of gas laws, obviously. So first off, we talked about units of gas. So common units, atmospheres, which is equal to 760 torr. That's equal to 760 millimeters of mercury. Remember that a millimeter of mercury is the same thing as a torr. It's a 1-to-1 relationship between those two. And we saw a lot of gas laws where we looked at the different variables, and different variables that we oftentimes dealt with was pressure, volume, and temperature. And here, for example, we looked at Boyle's law, which dealt with pressure and volume holding constant temperature. And what we saw here was, as the pressure went up, the volume went down, pressure went down, volume went up. Again, sort of an inverse relationship. One goes up, one goes down. In terms of units here, pressure could be any unit as long as they're the same on both sides. Volume could be any unit as long as they're the same on both sides. We also talked about Charles' law, which is V1 T1 is equal to V2 T2. This is at constant pressure. And because it's at constant pressure, that means that our volume will adjust to keep constant pressure. And what we see is as the volume goes up, so does the temperature. And as the volume goes down, so does the temperature. The key here in this gas law and pretty much everybody else is our good friend Kelvin. He recognized the importance of minus 273.15 degrees Celsius as absolute zero. So pretty much every gas law does need to be in Kelvin in terms of the temperature. That is how in Charles' law we're able to maintain constant pressure. So pressure adjusts as the temperature adjusts, because as the temperature goes up, everybody should be moving around faster, causing more collisions. So the volume adjusts to give everybody more space, so the pressure remains the same. We also have Dilusix Law, which is P1 T1 is equal to P2 T2. Same thing here. We're going to have our temperature in Kelvin. Pressure could be any unit you want. Here, this is going to be at constant volume. So here we don't have the volume adjusting. So what we see is the pressure goes up as the temperature goes up. Pressure goes down as the temperature goes down. Again, we don't have that volume in this situation adjusting. to basically allow us to maintain that constant pressure. We also talked about our good friend Avogadro. Again, he had a number, but he also had a law, which is V1, N1 is V2, N2. This is at constant temperature and pressure. And basically, N is the number of moles of the gas. We also saw sort of a unique relationship here is as the volume increases, so does the number of moles. And we could actually relate this to gas stoichiometry when we're involved with a reaction that involves gases. Instead of doing a mole to mole relationship, we could do a volume to volume relationship if we're at constant temperature and pressure. So again, got to be at those conditions. We could say, for example, 2 liters of A reacts with 3 liters of B instead of like 2 moles of A to 3 moles of B. We could also say 2 liters of A produces 4 liters of C on our product side again. And we could kind of do a stoichiometry problem involving gases where we don't have to use ideal gas law, and we could kind of just do a volume to volume relationship. Any questions on those laws there? Continuing on, kind of putting those guys together gave us the big guy there, which is the ideal gas law. The ideal gas law, which is our PV is equal to nRT. Remember, this is different as it's one set of conditions. It is also the most restrictive. Pressure here does need to be in atmospheres. Volume has to be in liters. N has to be in moles, and T has to be in Kelvin. And that's because R, which is the gas constant, 0.08206, has units of liters times atmosphere, Kelvin, and mole. So remember, you could always sort of find the units needed by looking at R if you can't remember it. We also talked about STP, which is standard pressure and temperature. And remember that when you're given something at STP, that is actually values. That is 273 for the temperature, and pressure is actually 1 atmosphere. And there is a special relationship that when you are at STP conditions, 1 mole of any gas will equal 22.414 liters. So that's like a conversion factor that, again, you can only use if you are at STP. And that will allow you to not necessarily have to use the ideal gas law, but remember that if you are not at STP conditions, you have to use the ideal gas law. You can also use the ideal gas law under STP conditions. All you simply need to do is basically just plug in 273 for the temperature and 1 atmosphere for the pressure. We also had the combined gas law, which is our P1 V1 T1 is equal to P2 V2 T2. Again, here our normal Kelvin on our temperature. Pressures could be any units, volumes can be any unit. And again, this sort of allows us to figure out what's happening as we sort of play with all 3 variables together. Any questions on that there? We also talked about in the gas chapter ways to calculate things like the density of a gas. And the density of gas is pretty much the pressure times the molar mass divided by RT. You also can figure out the molar mass of a gas. Remember, molar mass is usually grams per mole. And you could do that kind of figuring out the density RT over P. Remember that when we do density of gas, it's actually grams per liter, not milliliter. Remember that all of these guys are really based off of the ideal gas law. And you could do some rearranging of the ideal gas law and solve for N over V, for example, which will be P over RT. Remember that N over V is moles over liters, which is the molarity of the gas. And at this point, you could use the molar mass. And you could get yourself to grams per liter, which is the density. And that's essentially what this equation does. We could also use the ideal gas law for the molar mass equation. The grams are usually given to you in the problem. And then you could use the ideal gas law and solve for N, which would be PV over RT. And that would give you the moles part. So remember that you can't get to both of these guys really simply using the ideal gas law, and kind of do it as a conversion problem following the units, and you could get to each of those. Any questions on that calculation? We obviously talked about also as well in terms of gas stoichiometry, and much like all our other stoichiometry is really not all that different in our 4 basic steps here. We, again, going to balance the equation. We're going to convert to moles. And again, a lot of times you will go grams to moles using the molar mass and gas stoichiometry problems. But this is potentially a place where you could use PV equals nRT and solve for N up front and sort of use the ideal gas law up front in that problem. You again would do your mole to mole relationship. And number 4 here on the back end, a lot of times we're interested in gases, the volume of gas that would be produced. So we go moles to liters, which means we again here on the back end use our ideal gas law and actually solve for volume in this particular case. So again, really your same basic stoichiometry problems. Differences here is kind of the incorporation somewhere along the way, either at the beginning or the end, or I guess both places you could, I suppose, use the ideal gas law. Any questions on that there? We then talked about that oftentimes gases comes as mixtures of gases. And remember that when we have a mixture of gas, each of the gases that are flying around in that container, A, B, C, however many gases, they're all contributing really to the pressure. But there's a couple of things that are good. They're both in the same container in the same room, so they have the same volume and the same temperature, all the gases that are present. And remember that the total pressure is equal to the pressure of each of the individual gases added together, and that's what is referred to as partial pressures. How do we find the partial pressures? Where there's several different ways. One way is just simply use the ideal gas law individually for each of the gases that are present. And you could do that because one of the main things we talked about in terms of something being an ideal gas is that there is no interaction between one gas and another gas. So even though they're in there together, in an ideal situation, they can be sort of thought of as being in there by themselves. So basically you would just do the ideal gas law, add all of them together, get you your total pressure. If you don't have enough information to use the ideal gas law, maybe all you're given is how many moles of everybody and maybe a pressure. You could use another equation that we saw, which was this equation here. And this is the partial pressure of a gas. This is our mole fraction. And that is our total pressure. So this is a really good sort of equation to use when, again, you don't have maybe volumes or temperatures given to you, but you do have enough information about moles and some type of pressure, either somebody's partial pressure, somebody's total pressure. You're able to sort of use this equation. The last sort of partial pressure situation that we talked about was one where it's a very common in labs that we collect the gas over water. And the result of that is, as we're collecting the gas, say in this spot in our container, we're also getting some water that came along for the ride because basically the reaction evaporated off some of the water. We get some water vapor. So we get a total pressure in this situation, which is the pressure of the gas we're interested in, plus the vapor pressure of water. And that is the vapor pressure of water. And that is usually a value that you can look up and rearrange this equation and solve for the pressure of the gas, which sometimes is referred to as the pressure of the dry gas, because you're subtracting off basically water's contribution to the pressure. So those are three common sort of partial pressure situations that we talked about in terms of gases. Any questions on any of those things? Okay, so gases still going. We had some more stuff that we talked about in terms of gases. This is a big chapter. We talked about the velocity of a gas, the RMS. Remember, that is the root mean square velocity, how fast the gas is sort of moving. And that is equal to, and that's abbreviated with the little symbol there, the square root of 3 times RT over the molar mass. And again, a couple of important things here. Again, our R here is actually the one that involves energy, is this gas constant. And because we have the joules there, we come back to what we saw earlier, that the joule is a kilogram, meter squared, second squared. So what that really means is when we do the molar mass of this guy, it cannot be grams per mole, but it actually needs to be kilograms per mole so that these units cancel out completely. So when you do that, what you end up with is an R that basically is a kilogram meter squared second squared divided by a kilogram mole, and we're going to times it by Kelvin and divided by kilograms per mole. Your Kelvin per mole. Kelvins cancel, kilograms cancel, moles cancel. We have meter squared second squared, which gets the square root. And for our root mean square velocity, we end up with meters per second as our units that come out of that thing. We also talked about gas diffusion. Remember that when we have heavier gas molecules, they are moving slower than lighter gas molecules. So we could look at the rates, which are these, of 2 different gas molecules, and we could use it to figure out the molar mass, perhaps, of one. Or if we know the molar mass of 2 gas molecules and how fast one is moving, we could figure out, the rate at which the other gas is moving. But if you remember, really a lighter gas molecule will be moving faster than a slower one. And that's why, if you remember, we had that picture where I think it was like HCl and some ammonium chloride, I think, right? And basically the slower moving one was moving and the mixing was sort of occurring over here because the slower moving one was coming slower, guy was moving faster, and they start to mix. I think it was ammonia actually on this side versus our HCl. And it made ammonium chloride when it mixed. There you go. And so this guy was moving a lot faster because it's lighter. This guy's moving slower. They were mixing closer to that side because of how fast and slow they were moving. We also saw something kind of similar, which is gas effusion. And gas effusion is when basically molecule of a gas sort of escapes from one side to the other through a hole in this sort of container. And we saw one of a relationship that looks something like this, where we can incorporate time, and it's sort of our same sort of situation here is what we had. Molar masses is what these guys are. Now, we finished up the gas chapter sort of talking about the idea of real gases. Real gases are really when we get really high pressures or low temperatures. And remember that the kinetic molecular theory of gases, when we talk about an ideal gas, which behaves like the ideal gas law, when we talk about an ideal gas, there's basically two things that we don't take into account: the volume of the gas itself and interactions between different gas molecules. But under high pressure situations, that would mean, as we talked about, the volume is very, very small, which means those guys are going to be near each other for a lot longer time, and they're going to have to interact with each other. They're also going to have a big volume compared to the volume of the container there is. So the volume of the gas molecules are also going to be really important. And also the low temperature, they're going to be moving around slower, which means they will be in contact with each other for a lot longer as well. And these two things really don't hold up in that case. And we start to see, as we talked about, some deviations from the ideal situation. So if you remember, a guy by the name of van der Waals did some corrections to the ideal gas law, where you look up van der Waals constants with A as a van der Waals constant and B is a van der Waals constant. And we get this kind of scary looking equation here for a real gas or a non-ideal gas. This corrects the volume difference. I'm sorry, the pressure difference. This corrects the volume difference. Now, we talked about A and B, and those are van der Waals constants. And you do look it up based on the actual substance or gas molecule, and it is different values for different gas molecules. So as we talked about, under real gas situations, it's a very specific equation because A and B vary depending on the actual gas that you're dealing with. Most of the time, why we think of things in an ideal situation is under normal pressures, that is 1 atmosphere. If you remember that graph where ideal gas kind of goes this way, and we start to get some deviations, kind of moving this way. But most of the time, the temperature and pressures that we deal with is right about there. Actually, it's 1 atmosphere is here, I think, is right here. And even guys that would deviate aren't deviating all that much under normal conditions, which is why, most of the time we kind of deal with the ideal gas law. But again, under these really high pressure situations or really low temperature situations, you do have to kind of take into account some of these interactions. Any questions about gases? Okay, then we started to move into the home stretch here, and we started to talk about intramolecular forces and intermolecular forces. Intramolecular forces are forces that hold one molecule together. Like say sodium chloride, for example, are inside water here. The bonds between each of the hydrogens and the oxygen, the covalent bonds, are intramolecular forces. We focus mainly on intermolecular forces, and intermolecular forces are the forces that hold 2 molecules together. It could be 2 of the same molecules or 2 different molecules together. And these are the ones that hold one, for example, water molecule together with another water molecule, the force that holds those guys together. Now, water obviously is polar, as we talked about, so positive, negative, opposite attract. And the basis of all intermolecular forces, the basic attraction is positive and negative together is basically what holds that together, that electrostatic attraction. Intermolecular forces are always weaker than an intramolecular force. And that's, as we talked about in that simple example of when you heat something like water, the first bond that breaks is here. When we get water molecules into the gas phase, we don't break these bonds where we would get hydrogen gas and oxygen gas formed. Again, as we talked about a number of times, that would not allow you to get to probably the pasta making of the deal if you're boiling water in your stove, if you start producing hydrogen gas and oxygen gas. But what you do produce is separate water molecules from each other. So those intermolecular forces are always much weaker than any intramolecular force, like covalent bonding, ionic bonding, that holds guys together. Now, there's different types of intermolecular forces that we talked about. We talked about dipole interaction, and that is basically the main force between polar molecules and polar molecules. We also talked about ion dipole. That's between ionic molecules and polar molecules. A version of dipole is hydrogen bonding, and that is a bond between hydrogen and an electronegative element like nitrogen, oxygen, or fluorine. And that is what we see in water, basically. Got that bond right there. Positive, negative. Dipole again, they have fixed dipoles, so positive side, negative side of a molecule basically comes together. Ion dipole, ions surrounded by something like water when it dissolves. We also talked about dispersion forces, and dispersion forces are really the forces between nonpolar molecules and nonpolar molecules. And these are the guys that, kind of temporarily gain those things as one way. So kind of a nonpolar molecule next to a nonpolar molecule, the electrons could all kind of go this way, creating a temporary positive negative charge. And this guy would then also follow suit. And now it has a way to interact with each other through these sort of temporary attractions. In terms of strength of these guys, as we talked about, this is the strongest, this would be the next, and this would be the weakest out of all of them. Intermolecular forces are important because of basically being responsible for things like boiling points, melting points. The stronger the intermolecular force, the higher the melting point, higher the boiling point. The weaker the intermolecular force, the lower the melting point and boiling point. We also talked about cohesive forces and adhesive forces. And remember, those are our guys that, are responsible for things like the meniscus that we see, right? Here we have a stronger attraction between, say, if this was water and the glass tube than water itself. So we see the kind of rising on the sides of the water because of that attractive force. And that's why we always read from the bottom of the meniscus here, because really the water is filled to this level, even though it's kind of being drawn up on the sides there. Sometimes you have the attractive force between the molecule and itself greater than the molecule and something else. And that's like something like mercury, for example. The meniscus actually goes the opposite way because it kind of comes in on each other. And we end up seeing this inverse one. Same wing here, we actually read from the top of the meniscus here, because again, really the levels here, this is just being pulled down because of those sort of cohesive forces. We also talked about sort of evaporation, and why when we have sort of a puddle, there's a constant rate of evaporation happening and condensation coming backwards. But remember, we have air that blows it away. So over a big surface area, we're losing a lot of these molecules that cannot come back. And eventually, obviously, our puddle kind of goes away and evaporates. We see the same sort of thing happen when we put it into a beaker that's open. We get this evaporation, but not as to a great extent, because less surface area available here, a lot of guys buried underneath. So it does start to evaporate, but does take a longer time than, say, a puddle. And obviously, if we kind of put a solution in and pop a top on it, we will have a great, at first, rate of evaporation, but eventually it will settle down. And what we, as we talked about, we'll see probably a little bit lower level of the liquid at the end. We will have some vapor above it, which is creating vapor pressure, right? Which is the pressure of a vapor over a liquid. And we will get evaporation and condensation rates happening at the same time. We could actually calculate something like this using Redox law there, which is the natural log of the pressure of the vapor at the first temperature divided by the vapor pressure at the second temperature. And that equals the delta H of vaporization, which is the energy required to do the conversion of liquid to gas, just like the heat of fusion is the energy required to do the conversion of solid to liquid. And we could use some calculation. I think we did one maybe as well. That needs to be in Kelvin. That is R, which is our 8.314 version. That is in joules. That is usually in kilojoules. And you do want to be careful on that unit-wise that you don't run into any problems. Speaking of which, sort of the conversions that we talked about in this chapter, right, as we go from solid to liquid or liquid back to solid, that's where we have our freezing point, melting point occurs at the same temperature. And it just depends on sort of what you're doing as to what you will see. If you continue to put heat in, you'll go from solid to liquid. If you continue to remove heat, you'll go from liquid to solid. And for water, for example, that happens at 0 degrees Celsius for water. Not until you get above or below that that you technically do get liquid or solid to form. There is amount of energy required just to do that transition, not change the temperature, but take something, for example, water at 0 degrees solid to water at 0 degrees liquid, and that's the heat of fusion, and delta H is the enthalpy, if you remember. And for example, just off the top of my head, I think it's like 6.03 kilojoules per mole is for water. We also see the boiling point sort of happening as we go from liquid to gas, gas back to liquid. Again, for water, that occurs at 100 degrees Celsius. And again, it's the same temperature for both of those things where condensation would occur as well. And we have the delta H of vaporization that occurs. And it's approximately 40-ish kilojoules per mole. This is like roughly 333 joules per gram, 2260 joules per gram to do that transition. And again, you do see it takes a lot more energy to go from liquid to gas than it does to go from solid to liquid. When you go from solid to liquid, you're still together pretty close. When you go from liquid to gas, everybody's breaking apart 100% and flying around. So it takes a lot more energy to do that. Remember, the number is the same depending on which way you go. The sign is different. So it would be positive delta H of fusion going this way. Negative delta H of fusion would go that way. So positive 6 kilojoules to the right, negative 6 kilojoules going liquid back to gas. Positive here because it's endothermic for the vaporization. Negative value here because it is exothermic going in the opposite direction. Any questions on that there? We also talked about in that chapter phase diagrams, which very badly drawn, just like that, where we have basically solid, liquid, and gas happening. We have kind of pressure and temperature happening on the scales. And remember, we have our transitions as we go from solid to liquid. That's our melting and freezing. Liquid to gas, evaporation, condensation. Here where we go from solid directly into gas and backwards, sublimation and deposition. occurring, right? And that's evaporation, condensation, that would be melting, and that would be freezing. This is our triple point. That's where we have all three phases together. That's our critical point over here. Critical temperature pressure, where above that point, we have the supercritical fluid, where it has properties of a liquid, but kind of a flow of a gas, and so forth. Remember, typically speaking, 1 atmosphere is standard pressure. So if you go across in a straight line, we'll imagine that straight, wherever these crosses would technically be your melting point and freezing point here, and that would be really your boiling point that would naturally occur. Any questions on phase diagrams? Then we finished up sort of that chapter, I think, talking a little bit about solids. And remember, solids, they come together in a very organized fashion in a crystalline solid, which has a very long range of patterns and organization, as opposed to an amorphous solid, which has very little sort of repeatedness or pattern that occurs. And when we have a solid that comes together, like this, we can pull out really a section of it, which is what is referred to as a unit cell. And when we do that, we don't want to just take one where we just take a whole atom and go, cool, that's our unit cell, because it has really, again, no relationship to how it is oriented with its neighbors. So this is a very bad choice. We typically take, something that has a little bit of everybody, some neighboring guys, and we pull out a unit cell such as this, where we know, okay, if I just line up my next guy here, that guy's going to line up, that guy's going to line up. If I stack one this way, and can draw neater, this guys would line up. If I stack another one this way, these guys would line up. And you can see, you can start rebuilding really the three-dimensional shape of it just from that one piece of unit. There's a lot of different types of unit cells. We focused in on just cubic unit cells. And that's where the volume is basically the length cubed. And we use it to calculate something like the density of these guys, which is grams per liter. And there was a couple of 3 different types. There was simple cubic, which basically had one atom, which is 1/8 of an atom in each of the corners. The length of it is 2 times the radius. There was also body centered, which has 1/8 of an atom in each of the corners, which made 1 atom, and a whole atom in the center of the cube, which gave us 2 atoms total, which had a length of 4 times r square root of 3. And we had face-centered cubic cell, which had 1/8 of an atom in each quarter, which is 1 atom, and basically a half an atom on each of the faces, which gave us 4 atoms, and a length which was 2 times r square root of 2. Remember that when we do this to calculate something like density, we start with the atoms, and we take the atoms to moles using Avogadro's number, and from moles to grams using the molar mass. And that is basically how we get the grams part. The volume part comes from the length. We get the length, and we do want to get it into centimeters at some point. Once we do that properly, we then take the length cubed, and that will give us something like cubic centimeters. I'm sorry, grams per milliliter here. And that is obviously the milliliters or the cubic centimeters, which is more likely what the units would be. And that's how we get to basically our grams per cubic centimeters. Any questions on solids cubic unit cells? Okay, then we got into the last sort of chapter that you're responsible for in terms of the final, which I think is chapter 10. And we talked a little bit more about solutions and some colligative properties, but we opened up with the idea of why things are sort of soluble in each other or miscible in each other. Remember that we oftentimes use soluble or insoluble for like solids and liquids. We sometimes use miscible or immiscible for kind of liquids and liquids, really. So obviously, if a solid is soluble in a liquid, it will dissolve. If it's insoluble, it will not dissolve. And obviously, if a liquid is miscible in each other, they will mix and it'll look like really just one layer. And if they're immiscible in each other or insoluble in each other, we'll see layering happening. So if this was soluble or miscible, this would be immiscible, different layers sort of happening. We talked about what makes that happen, and it's really the intermolecular forces we talked about. And basically, it's the idea of like dissolves like. So what that means is if we take something that's polar and polar, they're good to go. They can interact well with each other. If something is ionic and polar, they could interact well with each other because they could use ion dipole forces. They could use dipole-dipole. They could use hydrogen bonding. And also if something is nonpolar and nonpolar, they are good to go in each other because they could use dispersion forces. So things that have very similar intermolecular forces have ways to interact with each other very similar to one another. Only run into a problem if we cross over polar and non-polar. Those guys have no long way of, still can't say that right, of interacting with each other over a long period of time. So they have no way to maintain that interaction, and they really will sort of separate out. We also talked about ways to classify solutions. There's saturated solution, which basically means we have the maximum amount of solute dissolved. We have unsaturated solution, which means that we are not there yet. So more solute will dissolve. And again, it will continue to dissolve until you hit a saturated solution. And then we also have a super saturated solution. And that's where we have too much solute dissolved in a solvent. And usually it's a very unstable solution, and you will start to see precipitation occur pretty quickly in that case. Any questions on any of those things? All right, just a couple more things to talk about. So I'm going to continue and kind of wrap up this chapter here. So if you want to hang out, obviously you're welcome to continue hanging out. Colligative properties is the main thing we sort of talked about here in this sort of last chapter. And really colligative properties are based on solutions and how many particles are dissolved in it. The more particles are dissolved in it, the more that they sort of get in the way of the normal processes of the solvent. So for example, the normal temperature at which the solvent would boil, or the normal temperature at which it would freeze, gets interrupted by all these extra particles in the way. And things like boiling points are affected, things like freezing points are affected. Vapor pressure as well is also affected by this. For example, the boiling point elevation, it actually elevates the boiling point, and we have this formula T, the change in the boiling point temperature is equal to KB times M. KB is the boiling point constant, and that is a value you look up on a table, and that is based on the solvent. M is our molality, which is our moles per kilogram. Remember that this is not the boiling point temperature, but this is actually the change in the boiling point temperature. And remember, because the temperature is elevated, that's defined as the temperature where the solution boils. minus the temperature of where the pure solvent boils. And as we talked about, that's really important to make sure that you sort of add or subtract correctly and get yourself to the right sort of value for that. We also saw the freezing point one as well. And that's freezing point depression. And pretty much the same formula, delta TF is equal to KF times M. Again, that is our freezing point constant, also based off of the solvent. That is our molality as well, moles per kilogram. This is depression, which means that the temperature will actually freeze less than it, which means this is actually the temperature of the pure solvent where it freezes minus the temperature of the solution where it freezes. Remember that we also incorporated into these when we have an ionic guy versus a non-ionic solute, it does make a difference. So if the solute is something like sugar, which is carbons, hydrogens, and oxygens, molecular, when it dissolves, you get sugar, one molecule, 1 for 1. If you take something that's ionic, like sodium chloride, when it dissolves in a solution, you get a sodium ion and a chloride ion. You get 2 ions for every one of these. And since colligative properties are based off of how many particles are present, you do have to adjust when your solute is ionic, and you do need to use I, which is the von Hoff factor. And it basically is determined by really the formula and how it breaks apart. So I would equal 2 in this case, as we talked about, barium plus a couple chlorides, I would equal 3 in this case. And they just really get incorporated into those formulas by just putting the I in front there, KFM, and for our boiling point as well. So for ionic compounds, you want to make sure that you do include that von Hoff factor that will take into account the extra particles that are basically there because of the ionic compounds and the extra ions that are present. We also talked about vapor pressure lowering, where we have the pressure of the component, the mole fraction of the component, and the total pressure. And again, you could calculate the vapor pressure of a empirical compound. And that is also lowered by it. Again, vapor pressure has to do with how many guys we get above the solution in the gas form. So obviously we have a lot of stuff dissolved in here. There's going to be less guys able to, again, get to the surface and get into the gas phase. And that means we're going to have less gas molecules above the liquid. Less gas molecules above the liquid means that our vapor pressure above the liquid would start to lower because of that. We also talked about osmosis. And osmosis is the process where solvent molecules go from really a concentration that is higher to a lower concentration. Actually, I just did that backwards. Let me say that one more time correctly. It goes from lower concentration to a higher concentration. Sorry about that. There we go. In an effort to sort of dilute down the higher concentration. So we talked about, if you had sort of a tube and that tube had a membrane in there, like a semi-permeable membrane. And on one side, we have pure water, which has no osmotic pressure. On the other side, we had something like salt water, which obviously if it's salt water, it has something dissolved in it, some particles. So natural flow of osmosis would be all the water molecules would head over to the right-hand side in an effort to dilute it. It will continue to flow until it hits something which is known as the osmotic pressure. And that's because basically atmospheric pressure is pushing back down on it, and it stops the flow of water molecules to the other side. We could calculate the osmotic pressure. If you remember, it really was just the ideal gas law. where we solve for P is equal to nRT divided by V. And if you remember, that is moles per liter, which gave us our molarity times RT. And if you remember, they used a different symbol for pressure. They used kind of like the pi guy, but it really is pressure. So that's the osmotic pressure, which is basically the ideal gas law in hiding, I suppose. But it basically can be calculated just using ideal gas law, which basically means, as we talked about, you do need to make sure that everybody's in the correct units and everything like that, like a normal ideal gas law sort of situation. Reverse osmosis, as we also talked about, is basically the idea where you basically apply a pressure greater than atmospheric pressure, which would then push everything back the other way. If you had a lot of good membranes and stuff like that to catch everything, you could end up with really pure water on the other side. Water, again, has no osmotic pressure because it has nothing dissolved in it. We finish up this chapter and really what you're responsible for by talking about three types of solutions: isotonic, hypotonic, and hypertonic solution. And isotonic solution basically exerts the same osmotic pressure as body fluids. Considered isotonic solution, 0.9% mass to volume sodium chloride or saline solution, which could be other type of ionic compound, or a 5% glucose solution, mass to volume. What that means is, if we take the classic example of a red blood cell, which sort of acts as a semi-permeable membrane, we will basically get flow inside and outside of the cell pretty much equal to each other. So nothing bad will happen. The cell will be okay. Hypotonic means less than hypo. So that is a solution that is less concentrated on the outside. And that means that basically what we will see is, by osmosis, because it's less concentrated on outside, everybody on the outside of the cell will rush into the cell. It will cause the cell to swell and burst, which is hemolysis, which is not so good. Hypertonic solution means more than. And what that means is, if we take sort of our red blood cells or membrane, outside of the solution is more concentrated than inside, which means this red blood cell decides, I want to try to dilute everybody on the outside. And that causes it to start to shrink and go through crenation, which is also not so good. So we do try to, obviously, when you give IV solutions, make them isotonic so you have nice and easy sort of relationships there. Any questions on this chapter? Okay, so that really does wrap up everything you're responsible for. The only thing left was kinetics, which, again, as I mentioned, I decided not to put on the final because we kind of finished it this week. So, and we're kind of over 1 o'clock here. So what I will do is wrap it up, I think, for here for now. Hopefully this